everyone, Mrs. H here again. Hard work continuing with the next section of Chapter 8, titled Catalytic Hydrogenation. This will focus on adding hydrogens across the double bond, so just thinking HH. The alkene is simply converted to the alkane. Notice that here is the ene and here is the ane. So thinking about how to add hydrogen to just go back to saturate the double bond. It will be stereospecific, being syn addition only, which we now understand is it will both be wedges or they'll both be dashes. And that's interesting because remember, we're adding hydrogen, so it's actually the hydrogens that went on as both dashes or the hydrogens went on as both wedges, but we don't draw the hydrogens, do we? So very stereospecific for only syn addition. We'll understand why when we look at the mechanism. And think about regioselectivity is not really a consideration here because we're adding the same element across the double bond. So since it's a symmetrical addition, we really don't have a regio center to worry about. All right, so adding HH across the double bond in a syn addition. The secret lies really with the use of the catalyst involved. And there will be two types of catalysts. One will be a heterogeneous catalyst and the other a homogeneous catalyst. Heterogeneous, let's learn, means it's different. It does not dissolve in the reaction medium. It's of different phase. Of course, the metal would be in the solid phase. And here you have the alkene and the hydrogens bonded to the metal surface. The metal acts as a binding surface for both the hydrogen and the alkene. So in other words, if hydrogen is not free to move around, and that's what we're adding across the double bond, it's fixed to the surface. We can only add it to the double bond from the double bond being reaching down to the surface of that metal, as I say, palladium or platinum. Palladium is most often used just because it's relatively cheaper compared to the precious metal platinum, but nickel is also shiny and can work as well. Syn addition occurs across the pi bond because that hydrogen is fixed to the surface of the metal, therefore it can only attach in one side only, a syn addition. So if we think about the syn addition of a hydrogen across the double bond, we have to think about chirality. If zero chiral centers form, syn requirement is not relevant. So for example, if I were to have simply ethene, and on the arrow you would see hydrogen and some sort of metal catalyst, you would now know that stereochemistry is not a consideration as you only form ethane and there are no chiral centers. If we have one chiral center formed, both enantiomers are possible. So think about, let's say 1-butene. Adding hydrogen across the double bond. We're going to need, that's not going to work. Let's make here, and then we'll have a branch. I have to make it unsymmetrical. So this will work. 1, 2, 3, 4, 5 in the longest carbon chain. So this would be 2-ethyl. And then you'd have a double bond and a 5-carbon unit, 1-pentene. So we're adding hydrogen across the double bond. Did we create a chiral center? Well, let's peek. Here we'd have 1, 2, 3, 4, 5 in the longest carbon chain. So we turn that into 2, oops, that's not the longest carbon chain. Here it is, 1, 2, 3, 4, 5, 6. So without the double bond, we find the longest carbon chain. At carbon number 3 is a methyl group, and that is just a 6 carbon chain now, so that's hexane. So the double bond must be in the longest carbon chain when naming an alkene, but since there is no longer a double bond in the product, we now find that we have a longer carbon chain by going to a hexane and labeling the methyl group at carbon 3. But what about the chiral center? Is this a chiral center right here? And the answer is yes. We have a methyl group in this direction, we have an ethyl group in this direction, and we have a propyl group in this direction, and of course not drawn but you know is there is the hydrogen. So that means in a syn addition, both possible enantiomers are formed, which means across the double bond in that original molecule, thinking about this carbon to this carbon, the hydrogen, let's say if it added as a wedge here, the hydrogen added as a wedge here, and meaning that the ethyl group must be a dash. That's one enantiomer. Or, in this example, let's suppose the hydrogens both added as dashes. Don't draw them, but you know is there. The ethyl group must be coming out as a wedge. We had a syn addition to consider. So you have a pair of enantiomers at the chiral center. If you have two chiral centers, the syn addition determines which pair is obtained just based on the stereochemistry of syn. And so with that example, I'll have some worked up and we'll go through those. How about right here? The syn addition to hydrogen of a symmetrical alkene will not produce a pair of enantiomers if it's a meso compound produced instead. So think about here, this would be a chiral center, and here is a chiral center, a syn addition where they're both, where the hydrogens, remember, added as both dashes, or if the hydrogens added as both wedges, these are the same compound. So the syn addition really just produced one compound that's a meso compound. A plane of symmetry has occurred. So in an anti-addition, you would have had one dash, one wedge. That's an anti-addition, and you could have a pair of enantiomers then. And these would technically be those pairs of enantiomers. But we only have syn addition, so they're both dashes or both wedges. Be careful of meso compounds when you have a plane of symmetry in the molecule. So let's predict the products of each of the following: hydrogenation with a metal catalyst. Let's try one. So I just want to figure out how long my carbon chain is. So here I would have 3, 4 dimethyl, and then at carbon 3 is the double bond. Excuse me. Excuse me, sorry. 3, 4 dimethyl, 3 hexene. I'll create 1, 2, 3, 4, 5, 6. There is my backbone at carbon 3, and at carbon 4 there is a methyl group. Do we have a chiral center? And the answer is yes. These are both chiral centers. And so we have to consider the syn addition. So when I redraw the two carbons that were in the double bond, right, those are here and here, well, the hydrogens could both land as dashes, meaning that both of these methyl groups were wedges. Now again, not drawn, but you know what I'm saying? The hydrogens both added as dashes. That's a syn addition. But that makes both the methyl groups wedges. and it's an enantiomer. I'm so sorry. 1, 2, 3, 4, 5, 6. If both of these methyl groups came off as dashes, not to draw them, but we know what that means is that those hydrogens both added as wedges. So that's the other enantiomer, the syn addition. And that's really what you're considering when you're writing out the stereo considerations. Look for chiral centers. And you see that based on hydrogens both being dashes or both being wedges, the enantiomers form syn addition. So we typically don't see these in the structure, so you have to imply that you see that they're there. How about you try one now? How about this one? Pause the video and give it some think time. Our longest carbon chain is a 4-carbon unit. And so therefore, in the presence of a metal catalyst, we have syn addition, meaning that we would add hydrogen either as both dashes or as both wedges. But are those chiral centers anyway? And the answer, of course, is no, they're not chiral, simply because these two carbons are attached to like groups, attached to like methyl groups. So you only have one product. This compound would have been named 1, 2, 3, 4. So it was 2, 3 dimethyl 2-butene. And the product that comes out, if you just think about, again, the longest carbon chain, it turns into 2, 3 dimethyl butane. That there's really no stereochemistry to consider because I did not create a chiral center. How did you do? These aren't bad, are they? Adding H across the double bond. So with a heterogeneous catalyst, such as the metal platinum, palladium, nickel, that was a heterogeneous because they were in different phases. A homogeneous catalyst is in the same phase as the reaction medium, and there is such a reaction medium using Wilkinson's catalyst, which is a rhodium compound. It does dissolve in the reaction medium and accomplishes a ligand with a metal. So just know that it really is the exact same outcome. You may choose to see the platinum, palladium, nickel, some kind of metal catalyst. No, that's a heterogeneous catalyst. Or you could see Wilkinson's, and that is a homogeneous catalyst, but the outcome is exactly the same. A syn addition is also observed, meaning that the hydrogens both added as dashes, or they added both as wedges when you create your chiral centers. Hydrogenation is a syn addition. So here we have an example of hydrogenation with Wilkinson's catalyst, where the hydrogen adds both as either dashes or they add both as wedges. But that is a syn addition. And here, of course, the alkene, as it adds hydrogen across the double bond, both as dashes or both as wedges. Just examples of how you don't see the hydrogen because you typically don't draw it. So therefore, it's the other functional groups that you're working off to prove that it is indeed a syn addition. Let's show a next type of addition called halogenation and halohydrin formation. So this section actually has 2 for the price of 1. Let's first consider halogenation, and then we'll look at halohydrin formation. So halogenation, adding 2 halogens across the double bond. Halohydrin will add a halogen and a hydroxyl group. So let's do the halogenation first. Notice that we're adding two like elements, just like we did with the hydrogen a moment ago. When you add two like elements, there really is no regio consideration, but there is definitely a stereo consideration. Now, the halogenation process adds across the double bond in the anti-position only. That means opposite. Notice that when one bromine adds as a wedge, the other bromine must add as a dash, and vice versa. Those are a pair of enantiomers. So the enantiomers that form are not syn, like in the last two examples, but they're anti, and let's learn why. The mechanism to explain the anti-addition only shows no carbocation intermediate. So very similar to how our borane, the BH3, was, as you think about how that formed a bridge, as did the mercury compound, we're going to see the same sort of mechanism for the halogen. So let's say the pi bond reaches out for a bromine and this bond collapses. That's a nucleophilic attack. And the leaving group leaves. That's the bromine. The bromine also has a set of electrons, just like the mercurium did. If we were to stop right here, this is a carbocation intermediate, and we would expect syn and anti both to occur. If a carbocation was present, we should see a mixture of all possible stereocenters, because it is just as likely to have the bromide attack from the top or the bottom of that trigonal planar carbocation. But that is not what we observe. Therefore, remember, the mechanism must explain the outcome. So just as that mercury compound created a bridge to prevent rearrangements in the formation of alcohols, the bromine does the exact same thing. So let's look at the proposed mechanism to explain the anti-attack. When the bromine is reaching out, see this double bond here? That's the rich pi bond, reaches out for the bromine. This is your nucleophilic attack, and this set of electrons on the bromine is actually going to form a bond, and this is a bridge, so there is no carbocation. Every carbon is 4 bonds. Now, this again, based on substitution, the most substituted bromine, that's where the nucleophile would then attack in the next step. The most substituted, here we have a symmetrical, so it doesn't matter. But notice that the pi bond up here, the pi bond is up, so the only place to attack would be from the bottom. And therefore you see your anti, an SN2 mechanism is always an anti-attack, right? We called it inversion if we were going to have a nucleophilic substitution. The SN2 100% has an inversion with the backdoor attack, chapter 7. So here's your anti-addition, and it's an enantiomer. So the bromonium ion that forms creates a bridge and prevents the carbocation formation. So in your toolbox, you are remembering the following 2 intermediates that are used to prevent rearrangement. The bromonium ion forms a bridge between the 2 carbons that were in the pi bond. That mercury formed a bridge between the 2 carbons that were in the pi bond. And remember that same mechanism, this was used to create alcohols. This is going to be used to create halogens. So with an anti-addition, Consider starting from the alkene. Here is the cis conformation of 2-butene. The anti-conformation would show 1 dash, 1 wedge as the pair of enantiomers. Now, if you started with trans 2-butene and did 1 dash, 1 wedge, you actually end up with a meso compound, and therefore you only have one. The same compound, meso, means that it's the same. There's a plane of symmetry. And so when you think about a meso compound, switching those over, it was only one enantiomer. Let's predict the major products for each of the following reactions. Give yourself some think time and come back when ready. Sitting on the arrow is bromine. We're adding bromine across the double bond. In our first example, the bromine is going to create an anti-addition. So think about anti-addition for stereoselectivity. So that means if this particular methyl group stays as a wedge, the bromine added as a dash. Down here, the methyl group would be the dash and the bromine would be the wedge. That is an anti-addition. Plus, it's an enantiomer. If the first methyl was the dash, the bromine here would be the wedge. And of course, down here, this bromine would be the dash and the methyl would be the wedge. Those are a pair of enantiomers. With anti-addition, 1 dash, 1 wedge at each carbon center, that's chiral. How'd you do for B? Well, in letter B, we'll redraw. We have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. Carbon 3 has a methyl group. So if that methyl group, let's make it a dash first. There's the methyl. That means the bromine would have been, the methyl group here is a wedge, so bromine is a dash, meaning that bromine would have to be the wedge here, and hydrogen the dash. And it's an enantiomer. Make the methyl group the dash, bromine the wedge, and of course the anti-addition would form the bromine as the dash up above. So those are your 2 enantiomers looking at the bromination across the double bond. This would work as well for chlorine as another halogen that we often use in halogenation reactions. If we use halogenation with a solvent such as CHCl3, a non-nucleophilic solvent, the bromine adds twice. So the solvent does not compete in the reaction. However, if we use a more exciting solvent, such as water, the water is actually the nucleophilic and captures the bromonium ion. So I want you to notice now, sitting on the arrow would be a water molecule as the solvent. And that means that instead of a next unit of bromine adding, we actually add the water across. And this was what we referred to as a protonated alcohol. So Halohydrin formation uses a solvent such as water, which is a nucleophile and captures the bromonium ion, still an anti-addition. And we would have to deprotonate in the next step. You would deprotonate that by using a water molecule, and this would simply be a proton transfer, and that bond collapses, and you can see your formation of the alcohol. So the water acts not only as a nucleophilic attack, it acts as a base to deprotonate the alcohol. Now, if you do not see water on the arrow, bromine adds twice. So when I see this, let's just have a double bond. And I see just, I was going to write H2, but I mean, let's say bromine. So you will end up adding bromine twice, and it would be in an anti position. But if we see on the arrow molecular bromine and a solvent such as water, we will walk through the mechanism a few times yet, but ultimately we need to walk away seeing that it is a bromine that adds and an alcohol that forms a Halohydrin formation. So water in the solvent is crucial in seeing a next step. Instead of the second bromine acting as the nucleophile, water acts as the nucleophile. It is a stronger nucleophile. So here's the outcome. When I have my bromonium ion, the alkene attacks bromine, expelling that as a bromide. Here's your bromonium ion. This prevents rearrangement, right? There's all carbons. So there's all carbons with 4 bonds. Everything is sp3 hybridized. The water then attacks the electrophilic carbon and forms a protonated alcohol. In the SN2 mechanism, remember, it's always a backdoor attack, an anti-addition. You'll then see water deprotonate the alcohol, and you end up with an anti-addition of a bromine and the alcohol. And the crucial thing here is seeing water on the arrow with the bromine. The hydroxyl will add to the more substituted carbon. Remember, bromine adds first, hydroxyl adds second. It's the hydroxyl group that is the nucleophile. Therefore, it will add to the more substituted carbon. Sitting on an arrow is bromine and the solvent water. In the chain, we see the double bond, and the 2 carbons in the double bond are going to form a bridge with the bromine ion. So I just want you to think about that as the bridge. And just to back up, you can see that this bridge right here kind of makes sure that both carbons are attached to 4 bonds. So there is no such thing as a carbocation intermediate. Alrighty. And now at this position, the water acts as the nucleophile. That means that the more substituted carbon, which is more electrophilic, is going to be attacked by the water molecule. Which means out comes right here the protonated alcohol, and that's an oxonium ion carrying a positive charge. At this point, the bromine is still over here. So you're looking at the nucleophilic attack, breaking this bond from that transition there, and the bromine attaches to the least substituted, and right now on the most substituted carbon, we have a protonated alcohol. So we'll need a next water molecule to act as a base, abstract this proton, and let that bond collapse. So that is a proton transfer. Remember this kind of thinking this through. This pi bond reached out for here, this bond collapsed. So that is a nucleophilic attack. 2 arrows required there. The leaving group leaves. Alrighty. And at this step, remember that you have a bromide that was from the leaving group. That's this guy. He's still there. But in a water, in the presence of water, you have a competing reaction. This right here, the water, can act as the nucleophile, or the bromide could act as the nucleophile. And we're just saying the water wins in this competing reaction. So we end up with a protonated alcohol, We need to deprotonate that alcohol, meaning this hydrogen will be abstracted and that bond collapses. And so ultimately, our OH added to the carbon that was most substituted, and the bromine added to the carbon that was least substituted. Now, let's determine stereo outcome as well. Do we have a chiral center? And it looks exactly like we do, yes. So with this addition, the Br and the OH must add anti. So let's redraw that, considering the outcome as anti. So I'm going to just redraw. If the OH was a wedge, meaning the methyl group must be a dash, then the bromine must have added as a dash. That is an anti-addition. And it's an enantiomer. If the bromine added as a dash, the hydroxyl group added as a, that's a wedge, duh, and here's your dash. That means the methyl group is now a wedge. Those are the two stereo outcomes for that particular reaction. So making sure that you see the anti-addition of OH and Br across the double bond when we have stereo outcomes to consider. How'd you do? How about trying some more? Predict the major product that are expected when each of the following alkenes are treated with bromine and water. So you will see this on an arrow as Br2 and H2O. I want you to remember that as you're going to add a bromine, and that's going to be to the least substituted carbon. And you're going to add an OH, and that will be onto the most substituted carbon. That's the outcome of bromine in water solvent. Alrighty. So when we think about that, let me count. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. At carbon number 3 is an ethyl. When bromine adds first, it will form on the least substituted, meaning the hydroxyl will come out as the most substituted, and making this guy a wedge. And 1, 2, 3, 4, 5, 6. Bromine could add to the least substituted carbon as a dash, meaning the ethyl group would need to be the dash, so hydroxyl is the wedge. There's your anti-addition of hydrohalogenation. In letter B, the double bond here, the hydroxyl group adds to the most substituted carbon, the bromine adds to the least substituted carbon. Then consider stereo outcomes. So in the first carbon, let's make the hydroxyl a wedge, so the methyl will be a dash, and therefore next door the bromine would be the dash. That's an anti-addition. Hydroxyl wedge, bromine dash. And if the methyl stayed as a wedge, hydroxyl would be the dash, and then bromine would be the wedge. The bromine and hydroxyl group added with an anti-addition. So a pair of enantiomers there. Did you get it? I hope so. What about anti-dihydroxylation? Anti means adding opposite, one dash, one wedge. Think of that as anti. And if you hear syn, they'll both be dashes or both be wedges. You'll have them both be the same. Alrighty. And then it says dihydroxylation. That means adding two OHs. Across the double bond, each carbon receives an OH. So a number of reagents can be used to carry out this transformation. Some will provide anti and others provide syn. This section will look at an anti-addition, and in the next section we'll devote to a syn addition. Alrighty, so anti first. The anti-addition for dihydroxylation involves a very strong oxidizing agent known as a peroxy acid. Think about this. Peroxy acid has a carbonyl group along with 2 oxygens before the hydrogen, a very strong oxidizing agent, even stronger than the peroxides we were looking at earlier. The peroxides had the OO. This would be an alkyl peroxide. This is called hydrogen peroxide. But these were also very strong oxidizing agents. A peroxy acid has the double oxygens as well, but it's next door to a carbonyl, which makes it even a stronger oxidizing agent. Here's peroxyacetic acid, having 2 carbons is the acetate base word. And here's meta-chloroperoxybenzoic acid. Again, 2 carbons in that chain there, benzoic acid. Very strong oxidizing agents. In the presence of this peroxy acid, very unique, kind of very interesting mechanism. The peroxy acids convert into carboxylic acids, and it gives the 3rd oxygen to the pi bond of the alkene, creating an epoxide intermediate. So think about what we just said. Let's draw a cyclopentene. Just draw that there. And let's just take a look at the peroxy acid. Remember how it had 2 oxygens in a row that led to a carbonyl that led out to an R group. The pi bond is going to go after the oxygen right here. This bond then collapses over here. And this bond, notice here, it's going to just pick up and put those as electrons. And we create this beautiful transition state where the oxygen, these are just bonds. So if you think about the pi bond now disappearing and forming just attachments to this oxygen. Those are both leading out to the oxygen that was in the original acid, right? And so these are all just delocalized bonds now. I'm going to highlight where that's coming from. The peroxy acid, that additional oxygen, is now attached to both carbons that were in the original pi bond. Those are the vinylic positions carbons. And then through this transition state, I should draw that like this because it cannot be isolated, it moves to a true intermediate known as an epoxide. Now, the epoxide leads out both wedges or both dashes to that oxygen, and then of course you just regenerated the carboxylic acid has now been regenerated here. So the peroxy acid, that's this guy, really takes one of these oxygens and creates a bridge between the 2 carbons. It's called an epoxide because it's a 3-membered ring. Where oxygen is one of those. So when you hear epoxy or epoxide, it's a 3-membered ring with an ether linkage, ROR, where the oxygen is now just saturating both of those carbons to make sure they have 4 bonds. So there's no carbocation intermediate. Notice that this bridge, this epoxide bridge, prevents any sort of rearrangement, right? So now we're going to go through a proton transfer where I can take the acid proton, that bond collapses, and then you can see the beginning of the alcohol right here. And the unique part here, the water will then serve as the nucleophile, and you see how it's coming underneath. That's an SN2 substitution. So therefore, when we look at the SN2, remember that it's always a backdoor attack. This right here is now the protonated alcohol. We need to get rid of that extra hydrogen, and you do so by using a water now as a base to deprotonate. And notice what we've got here, an OH, and an anti-addition. The epoxide intermediate ends up to be one hydrogen facing the top panel. The water will come underneath to give you the bottom attack. You deprotonate the water and you end up with two groups of hydroxy. And the trick here is to remember it's the bridge formation. That should look familiar. A protonated epoxide forms a bridge, no carbocation. Here's the two carbons that were in the pi bond to begin with. A bromonium ion forms a bridge, no possible rearrangements. And the merconium ion formed a bridge, no possible rearrangements. These are three similar intermediates now in our mechanism tool bag, all explain the anti-addition for an SN2. Remember, the SN2 is always a backdoor attack, a bimolecular collision, where bonds are breaking and new bonds are forming all the time. So let's use this. Let's predict the major product for each of the following reactions. Step one, I want you to notice that it's a long coup, isn't it? That this is called a peroxy acid. The peroxy acid, COOH, that's an additional oxygen. And this is the oxygen that is used to form the epoxide intermediate. And so when you redraw this structure, thinking about intermediates, the carbons form this epoxide intermediate. That's this guy right here, the protonated version, which will happen in the next step. So remember the mechanism. You first form the epoxide, and then it begins to protonate in the acid catalyzed opening of the ring. And that's exactly what happens. That's a good point to emphasize. The protonation opens the ring. So thinking that through, what did we have form? That backdoor attack. When you have this epoxide, it then reacts with a water molecule. Well, that's this proton here. And what you see happening is a proton transfer, and then you get this protonated epoxide. And that's this visual that you had on this slide, this epoxide. And that positive charge is based on oxygen having 3 bonds and 1 set of dots. Alrighty. So the 2 carbons that were in the double bond are held together by 2 wedges leading out to the oxygen. We formed a protonated epoxide intermediate. Then what? Do you recall from your mechanism? This protonated ring needs to be opened. So the water is going to act as a nucleophile and attack the most substituted carbon. Here it's symmetrical, but it would attack the most substituted carbon and therefore open the ring. So in this next example, our water molecule is going to undergo a nucleophilic attack to the more substituted carbon. So right here is the nucleophilic attack. Whoops. Thank you. And as I think about drawing that, the ring then opens. And when it does so, let me get my carbon drawn. Here now, on the least substituted carbon, is the opening of the epoxide. And over here, on the most substituted, you have the protonated second alcohol. We need to deprotonate that, so this will be a proton transfer where the oxygen reaches out for the proton and this bond collapses. Now think that through. If this hydroxyl added as a wedge, this hydroxyl must add as a dash, and making one of these, I'll make this guy the wedge. And if this hydroxyl added as a dash, this methyl group would be a dash because this hydroxyl will be a wedge. Whoops. Oh, let me redraw that. Sorry. The methyl group is now the wedge, and here this guy has to be the dash. Anti-addition. Alrighty. So that methyl group will be in one situation the dash, in the other situation the wedge. An anti-addition. This epoxide ring prevents a carbocation from forming, the epoxide ring, and the ring opens through the attack of a water molecule on the most substituted carbon. So when that ring opens, the first hydroxyl is on the least substituted, and the second protonated hydroxyl is on the most protonated. And remember, regiochemistry is not truly a consideration because we're adding the same hydroxyl group across. The epoxide ring, just as our bromonium ion and mercurium ion, all three of those had the same very similar mechanism, forming bridges with those carbons in the pi bond, and therefore no carbon cation was formed. When you see anti-addition, you're adding two groups of hydroxyls. Look at this as the peroxy acid. That's got to be your indicator. That's a very, very strong oxidizing agent. And when I see that, think about its functional group. You have an OOH. It is this oxygen right here that when I highlight it, that becomes the epoxide intermediate. And so just thinking where that bond occurred, this oxygen, that is the epoxide intermediate. And let me just highlight it the same color so you can see where it ended up. And through that you can see that you'd regenerate the carboxylic acid as well. Alrighty. So just to emphasize where that oxygen came from, it's at this particular center, matching this oxygen here. And just putting back to the pen as best as I can. Yeah. Then we're going to just regenerate the RC double bond O, OH. That really is just the carboxylic acid COO. When I remove the extra oxygen, it creates this epoxide intermediate. That then is going to be the source here where the acid is then used, and that reaches out to create a protonated epoxide. Just emphasizing this important part. And this then, that protonated epoxide, that will now serve as the ring opening when water attacks. So in that next step, thinking about water as a nucleophile, it's going to attack the more substituted carbon and the ring opens. When that ring opens, right here we form the first of the alcohols. And so here, this was pointing down a moment ago. This now is the opened ring, the epoxide. And of course here is the protonated alcohol that then gets deprotonated with a water molecule. So just emphasizing it's an anti-addition. Make sure that you see that the epoxide ring prevents any rearrangements. What is the outcome? It really doesn't ask us for mechanism, but we can certainly chat about it just to help emphasize. Notice what I'm seeing, a peroxy acid. You have to recognize a peroxy acid is one that has RC double bond OOH. That's a peroxy acid. That is going to form an epoxide intermediate, and that epoxide intermediate then opens the ring and another alcohol will add on. So what is the outcome? Across the double bond is an OH. As I think about stereochemistry, we will consider that if this hydroxyl added as a dash and a wedge, and the opposite would be true. So adding two hydroxyl groups in the anti position using the epoxide ring intermediate, the ring opens to create a spot for anti-addition. How about another? Oh, we did that, didn't we? How long have we been talking? Oh my goodness, 51 minutes. Let's go through the Sin-dihydroxylation. You may certainly pause the video at any time and take a rest, but since we're adding dihydroxyl groups, we did let's keep going just quickly for Sin-dihydroxylation as well. And there's two reagents that are used to do this. One of them is called osmium tetroxide, OSO4, and the second is potassium permanganate in basic conditions. So sitting in the first step, you would see osmium sitting on the arrow here, OSO4, and then you'd have a workup of sodium sulfite or sodium bisulfite. And across there, we add Sin addition, so both hydroxyl groups come out as dashes or both will come out as wedges. In the second, potassium permanganate, notice this is a very similar setup. One has the center group of osmium, the other is the center group of manganese, Mn. And we end up with about an 85% yield of Sin addition in a basic workup. So let's compare those two reagents. Osmium tetraoxide, very expensive. Osmium compounds are also known carcinogens. So highly toxic. Osmium is carcinogenic. They can be coupled with a co-oxidant and regenerate the osmium so that once you buy it, you don't have to keep buying it. You can use it over and over and over again. Potassium permanganate in the basic conditions, well, it's very inexpensive, but sometimes hard to control. It's such a strong oxidizer that it often causes further oxidations of the diol into carboxylic acids. And help to run it cold helps to prevent the further oxidation. So when you're thinking about first oxidation, when you would form two alcohol groups in the Sin addition, what can happen sometimes is that they go on even further and oxidize more by forming carboxylic acids, and that's hard to control. It's such a strong oxidizer. Running it very cold helps to eliminate this next step, so that's why you'll often see very cold temperatures. But with the osmium sitting on the arrow, the double bond will have a Sin addition guaranteed. So even though it's expensive, even though it's highly toxic, it's still the choice tool for organic chemists who want a Sin addition diol to be achieved. So what is the outcome when I see osmium tetraoxide? That double vowel is sometimes alleviated and you just say tetroxide. Well, it's a Sin addition where the hydroxyl groups are going to add in the same fashion. Now, of course, I'm just emphasizing that you would have two enantiomers form in the syn addition, both be wedges or both be dashes. But a diol is produced. Is how you would write that. And then of course we would have to consider at carbon 2 and carbon 3 are our stereo centers. Looks like priority 1, then priority 2, priority 3. That's spinning in a clockwise fashion, so that is an R configuration. And over here at carbon 3, priority 1, 2, 3, that's also spinning in the R configuration. And then of course in the opposite you would have its enantiomer would be 2s, 3s, 2,3-butane diol, a pair of enantiomers formed. Same idea. Here we're having a workup of osmium tetraoxide. The diol will form. You will have a syn addition, but if it's on the tail here, is really no dash or wedge because there's two hydrogens as well. So with one chiral center, you would have one, and then this guy would just be in the same plane, because notice that's not a chiral center, so no need to talk about it. Not a chiral carbon at the end. All right. Even if you see potassium permanganate, notice that it's running cold. It's the same outcome. Cold helps to prevent further oxidation, so it is important. You would have a syn addition across the double bond and its enantiomer. Let's pause our video here. We've done some great work. It's time to rest a little bit. We'll have one more video kind of bringing further information kind of to closure. All right, take a little break, come back when ready.